Yeah, you need it like that, you know?
Yes.
I really didn't know.
So for this one, it says X represents the number of years since the baseball card was issued. Use the remainder theorem to find the value of the card in 1999. So that means what I'm really looking for is f of 10. And it says to use remainder theorem, which means what I'm actually going to do is I'm going to put 10 on the outside. I'm going to divide, and then I'm going to take the remainder as the answer. No, it's positive. That would give me 2, which would give me 1.75, which would be 17.5, which would be 20.5, which would give me 205, 209. So to answer that question, 209, whatever it was they were talking about. What? What? Dollars?
No.
Dollars.
Dollars.
Dollars. What else from your homework? From my what? Rolling it. Rolling what?
Rolling money.
Like rolling in money?
Yeah. You rolling, Mr. McGee?
What do I do for a living?
Mr. McGee, I heard you gotta pull.
Good. Made 100. Made 100.
I think.
All right. I'm gonna rewind back ever so briefly to Algebra 2 for just a second to remind you of something. Let's say, this, by the way, we're going to be talking about Descartes' rule of signs. I know. It is not. But before we do that, I need to go back and remind you and refresh you on something from Algebra 2. If I have something like this. Don't write that yet. No, do write that. Okay. If I asked you to factor that, what would you do? Double slash? Is that what you said? It doesn't double slash. Not quadratic.
Just double slash it between the 3x.
What good is that going to do you there?
You can double slash it. And then you execute that, and then you have another one.
Y'all, there is no double slash.
I would hit the double slash.
You do what? Okay, I think that's Descartes. We're going to do that for a little while, but we haven't got there yet. But I'm talking about back Algebra 2. What would you do to find the factored form here? Fully factored form. That doesn't work.
You can't do nothing.
Okay, let me reword it. Find all the zeros without a calculator. Oh, you plug in. Okay, find the y'all. Come on. Right, but when I plug it into zero, I'm going to have to factor it. How do I factor this?
That's the answer.
It's the PRZ. Okay. They who?
National Association of Mathematics.
PRZs are possible rational zeros. And tell me this. Where do I get this list of possibilities? Divide what? Everything what? No.
Divide all over. I don't know what that is.
We take all the factors of the constant and divide them by all the factors of the leading coefficient. Do you guys not remember listening? All right. So the factors of the constant. Tell me, what are the factors of 8? In order, go in order, small strings. 1, 2, 4, 8. And I'm going to go a step further and put a plus or minus in front of each. For the leading coefficient, it's just 1. So my possibilities, that means it may or may not be a 0, are going to be, so this is my list of possibles. Maybe it is, maybe it's not. We're going to test them, but in just a minute. But my list of possibles are going to be all of these divided by 1. Then I would take all of these if there was another factor here, and I would divide them by the next factor, right? Just to get that list of possibilities. So now my question to you is, if those are possibilities, how do I find an actual 0? Okay, you could plug in, and if you plug in, what are you looking to get to know that it's a 0? 0. But really, what are you doing? Think back to that remainder theorem we just did. Whether they're factors, so how could I test that? Synthetic division. That is a lie. Let's start. We do it until we find the one that works. We just need one to start with. We need something to spring. Well, but that's a good point, is I could use my calculator as a springboard to find one to test that would probably work. What do you got? I'm going to divide first by positive 1, then by negative 1, then positive 2, then negative 2. It's coming from this list. I'm going to do all of these. But Dozier is actually putting this in his calculator to give us a good springboard number to check. So because instead of testing every single one, I'm going to get one that looks like it's right from the graph and just double check so I can get it factored down to where it crosses the X. Okay, so let's start with the positive 1, okay? Positive 1. So when I do this, I should get a remainder of 0. That's how I know it's a factor or a 0. All right, so I get 1, 1, negative 1, negative 1, 2, 2, negative 4, negative 4, negative 8, negative 8. I should have 5 zeros actually altogether. But some of them might be imaginary, I don't know. All right. All right. Yes. The constant and the leading coefficient. It's a combination of all fractions you can make out of those values. It's just our leading coefficient was 1, so it made it really. If the leading coefficient happened to be 2, then my possibilities would be the same thing, but then it would also be 1 divided by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. 8 divided by 2 is 4. It would just add that 1/2 in there. Yes. Yes. Right. What you confused about?
So you get the list of possibles.
Yes.
But it's just like the list of possibles.
And then you take that list and you divide them by every factor of the leading coefficient. Ours is actually. Yeah. That's not, they were saying, what if there was a number instead of 1? So what if it was 2? If it was 2x to the 5th plus 8, well, then my list of possibilities would not just be these, but then I'd have to take all of these and also divide by 2, because I divide all of these on the end by 1, but then I also have to go back and divide them all by 2. But we're trying to kind of shortcut. Did y'all do this at all? You did.
I don't remember.
We spent a long time on this.
This was one of those ones that just went way over my head. This one ones where I played 7.
Okay, so watch. Why is this convenient? How does this help me factor, or how does it help me find the zeros? Well, because now I know if I get 0 here, that means x minus 1, I'm just going to write this as a multiplication problem, times x to the 4th minus x cubed plus 2x squared minus 4x minus x. Right? Can I factor now? Uh-oh, I still can't factor. I got to do it again. But I told y'all pre-cal is a lot of algebra 2, but harder. We can use the same factors, but now we can use a little bit shorter equation. So we can go from the same list of possibilities, but this is what's going inside our synthetic division now. Okay, so now on the outside, let's try that -1. We tried 1. Now let's do -1. And I'm using this one. Yep. 1, -1, 2, -4, -8. I'm going to drop, and I'm just going to run through this kind of quickly.
Alright, so why do you use -1?
That was from our list of possibilities over here. I'm still pulling from that list of numbers. And Dozier said he graphed it, and it looked like it crossed at 1 and -1, so I thought it'd be a good one to try. So now, okay. So now write it as a multiplication problem, as a factored multiplication problem. I've still got this x minus 1 out here. But now what does all of this tell me? X plus 1 times what, Miguel? Uh-huh.
-8.
Now you can slash it. You absolutely can slash it now. Now I can come through. If I couldn't, guess what I'm doing again? PRZs again. I'm going to continue PRZing until I find what works. So, okay, well, this is not the homework. I haven't showed you the homework. This is what you have to remember from Algebra 2 to do in order to do the homework. The new stuff's not hard. The remembering. Why'd I put what, Kate? I'm sorry. So the x minus 1 came down from this first part. The x minus 1, the x plus 1 is coming from where I divided by -1 here. And then this one is coming from all of this on the bottom. I divided. Did you get it fully factored? Slashed it down. Take out an x squared, take out a 4. It leaves me with x minus 2. Why? But I can solve. Why is it trash? It's imaginary. You're exactly right. That's okay. Why is it not? I'm supposed to... How many? Oh my gosh. How many solutions am I supposed to get? 5. 1, 2, 3, 4. None of them came out to be I on this list. Did you?
Yeah, that's called I.
I'll look and see. I don't remember getting any eyes, but I'll work through it fast. I'll look and see. No, you might not have. I'll look at it. Anytime you if you take the square root of a negative number, it just has an I on it. That's all it is. That's all you have to know with the eyes. It's imaginary. Do I?
Do it in a drum.
What? They're not real.
Exactly.
A negative, it's only imaginary if it's a negative under the radical. Oh, that's fine. That's fine. Right, because look. Okay, I show you all that to remind you. You'll have a few of these tonight, okay? But I show you all that to remind you that now of the how to do the PRZs. But let me show you DesCartes. DesCartes is a lot easier than this is. You see how, depending on my leading coefficient or my constant, I could get into a big list of possibilities, right? So what DesCartes does is DesCartes narrows that list of possibilities for us. All right. Y'all done with this? Yeah. All right.
That's just making a prescription drug.
Let's look at that same one we just did. Now, you're going to have to make sure all of your exponents are accounted for. So check and make sure you don't need any placeholders before you start this. Looking at this original equation, how many times does the sign change consecutively? Like I go from positive to negative, that counts as 1. I go from negative to positive, that counts as 2. Positive to negative counts as 3. How many times does it happen altogether in the equation? 4. This doesn't count because it goes negative, negative, and here this counts as 4. What this tells me, every time the consecutive signs change, okay, in my original equation, that tells me it tells me how many positive zeros I have. I have either 4 or 2 or 0. I keep going down by 2 until I hit 0. Okay? That's what DesCartes says. You may like it and you may not, but I have to show it to you. Huh? Oh, yeah, because see, it's negative, negative. It has to go from negative to positive or positive to negative. It's the total amount of consecutive sign changes. No, it goes from positive to negative, negative to positive, positive to negative. This is negative to negative, but then this one is negative. Okay, but beside each other. Total sign changes then, if you want to, yeah. Okay. Now, does that hold true? And listen, if I got that it was 10, then it would be 10 or 8 or 6 or 4 or 2 or 0. You go down. How many positive zeros did I have when I solved it? 1, 2. Does that fit? No, positive zeros. Those are imaginary. Those aren't real. Those are imaginary. All right. Now, that's half of DesCartes. Here's the other half. Okay, so it's the number of sign changes or, and then you keep subtracting 2 until you hit 0. And it tells you how many positive solutions you get. We'll do another example of this in just a minute. Let me show you the negative. Huh? Or. Yeah, it's or. You keep subtracting 2 until you hit 0. So it depends on what you start with. You keep doing that until you hit 0. If I start, let's say I started out with 20. If the sign changed 20 different times, then I'd have 20 or 18 or 16 or 14, and I'd go down until I hit 0. Yeah. Still by 2, and so you'll end at 1. You can't go negative. So let's say 11, then I'd have 11 or 9 or 7 or 5 or 3. Because you're saying this is not the solution, this is how many solutions. Okay. Go ahead. Yes. 4 positive solutions or 2 positive solutions or no positive solutions. Yes, that's exactly right. The negative solutions, I put a negative in for every x. Okay, so if I do that, now what you have to think about here is your power on your x, right? If I've got an even power, it forces positive. If I've got a negative power, it keeps the same sign, right? Not a negative, an odd. Does that make sense? Negative 1 to the 3rd power is, but negative 1 to the 4th power, positive 1, right? So if I put a negative up in the same equation for every x, right? That means this would be negative x to the 5th. Does it change the sign on the power of 4? No. It is a little crazy. Okay, this, here's your in a nutshell. It changes the sign of every odd power. It keeps the sign the same for every even. Every time. All right, so this is still, the even one's going to keep its sign. I'm fixing to show you. The odd is going to change. The even keeps its sign, the odd changes. Constant's just going to stay the same, it doesn't have an X on it. How many times does the sign change on this one? One. I should have, I can't say -2 because I'm already as low as I can go. It should have exactly 1 negative solution. Does it? Look, there's 1 negative solution. So you're going to have a set on your homework where it's literally, you're not finding the solutions, you're just telling me how many positives and how many negatives. And you're just looking at how many times signs change. Sorry, y'all have a little bit of homework tonight. Yeah. Yeah. All right. Let me do one more example with you so you can see.
So there's only one jump. There's just one negative. So if there's 3 jumps, there'd be 3 negative solutions.
Say that again?
If there was 3 changes, then it'd be 3 negative solutions.
3 or 1.
3 or 1.
Right. I'm fixing it. I know. I'm fixing it. And I'm going to cut some of it out.
Good. Let's just do the first 3.
Because those have even exponents, if you plug a -1 in and you raise it to an even exponent, it doesn't change the sign. Because -1 squared is positive. Look at this one. This is 11. Tell me how many positive solutions and how many negative solutions this would have. Positive's going to be 2 or 0, right? And then for negatives, remember the sign of every odd exponent's going to change.
This doesn't take that much room.
For DesCartes, this is all you do. Okay? That's the point of DesCartes. That's the new stuff. So here's what I want you to do. I want you to do numbers. Yep. I want you to do number 1 and 3. That's a full PRC workup. Yep. 1 and 3 on your sheet. That's a full PRC workup. What difference does it make? They have the same degree. It's just you're going to have placeholders in there. You're gonna... Okay, do 2 and 4 if you'd rather.
Half 1 through 4.
Pick any 2 you want, 1 through 4. How about that? Pick 2, 1 through 4. Pick 2. No. Then 5 through 11, I just want you to do this. I don't want you to go through the whole PRZ workup. We'll do that on some stuff. I don't want you bogged down tonight, okay? That's not the point of this. This is the new stuff. If you struggle with PRZ because you don't remember it and you don't remember how to do it, go back and work the others and work on PRZ. But if you got that from Algebra 2, there's no sense in beating a dead horse.